All right, welcome. We're going to do a couple more. I'm actually, you know what, I was going to do it. I have this whole thing planned out, but we're going to do it the easy, quick, dirty way. Let me just show you what I mean. So we're going to take the Laplace transform of sine of bt. Okay, so the Laplace transform of sine of bt of s is equal to the integral from 0 to infinity e to the negative st sine of bt dt. Okay, so now I have this whole thing written up, this really ugly integration by parts. You know, you have to do it twice. You all know the deal, right? You have to do the integration by parts twice, make sure. I'm going to show you guys a way around that, okay? I'm going to show you guys a way around that, at least in this case. So, and in fact, we're going to get two Laplace transforms. We're also going to get cosine of bt of s. Okay, so that's going to be the integral of 0 to infinity e to the negative st cosine of bt dt. Okay, so it's going to use Euler's formula. Do you remember Euler's formula? Euler's formula was e to the I, in this case bt, is cosine bt plus I sine bt. Okay, so what we're going to do is we're going to say e to the I bt e to the negative st, and then integrating from 0 to infinity in t should equal, okay, well, it should equal L of cosine bt plus I times the Laplace transform of sine of bt. And the thing is this integral is a lot easier to solve. Okay, so let's go ahead and solve that integral. By the way, if you want to solve these by integration by parts to check that you get the same answer we're going to get, by all means do so. Okay, by all means, I'm not stopping you. I'm just trying to show you guys another, just a little trick. Maybe some of my rigorous math friends would you know, shame me for doing this, but this works. Okay, so let's just do what works. Okay, so we're going to take this integral. This is the limit as t goes to infinity, 0 to t. I'm going to write e to the I bt e to the negative st dt equals the limit t goes to infinity, the integral from 0 to t. Now I'm going to have e, I'm going to put those together. So I'm going to put negative s minus ib t dt. Okay, so now I'm just going to use the formal thing, just like we did the other integral before. Okay, this is going to be the limit t goes to infinity, okay, 1 over negative s minus ib e to the negative s minus ib t, okay, t goes from 0 to capital T. Okay, so far so good, right? Okay, so there are some issues with doing this integral, but those issues are not something that we need to worry about at this level. Okay, at this level, we just want to get a formula that we can work with. Okay. Next thing we're going to have is we're going to take, and we're going to go ahead and plug in the answer, or plug in the limits. Limit as t goes to infinity, just like before, at 0, we're going to get 0, and at t, watch what happens. So we're going to get, I'm going to write this as 1 over s minus ib times 1 minus e to the, I'm going to write this like this, e to the minus st, e to the ib capital T. Now, what happens as t goes to infinity? This thing is cosines and sines, right? So that's bounded. Okay, that's between -1 and 1. But this thing is going to go to 0. Okay, because as you take t going to infinity, as long as s is greater than 0, so we need, at this point, we need to say, you know what? We need s to be bigger than 0. Okay, then this is going to go to 1 over s minus ib. Okay, so now we still have to rationalize this. We still have to rationalize this. In order to rationalize, that means we have to get rid of the I in the denominator. So we're going to multiply by s plus ib over s plus ib. Okay, so we're going to get s over s squared plus b squared plus ib over s squared plus b squared. And we've got it. So let me write these out, or let me copy these. This part, remember, is the imaginary part. This part is the real part. And if you calculate these integrals using integration by parts, you're going to get these answers. Promise, honest. Okay? All right. Let's go ahead and let's go to the next video.